Hello, my name is Jeremiah Blocki, and I'm excited to tell you about our work, DALock, Distribution-Aware Password Throttling. This is joint work with Wuwei Zhang. The goal of our work is to protect against online password attacks. To illustrate online attacks, suppose I register for an account with my favorite password, 123456. Once I create the account, I may use it to send messages, post photos, process financial transactions, etc. An online attacker tries to guess my password to access all of this confidential and private information. In this case, the attacker succeeds before he or she gets locked out. Password spraying is one example of a strategy that an online attacker might follow. In this case, the attacker attempts to log into many different accounts using a few popular passwords. In the example diagram, the attacker attempts to log into everyone's account using the same popular password. Online attacks are unfortunately a common privacy threat, as illustrated by the highlighted news clips. Unfortunately, online attacks can be surprisingly effective. Many user passwords are relatively easy to guess, as illustrated by the password word cloud here. In fact, nearly 1% of RockU users selected 123456 as their password, and similar findings hold for other breached password datasets. This means that even a simple password spraying attack can potentially be quite effective. The traditional defense against online attacks is to lock the user's account after k consecutive incorrect guesses. In this example, the attacker is locked out after submitting 3 incorrect guesses. The traditional k-strikes mechanism induces a classical usability security trade-off. Some have advocated for larger values of k, for example k equals 10, to improve usability. But this also gives the online attacker more opportunities to crack the user's password. Others would advocate for smaller k, for example k equals 3, to improve security. But this increases the chances that the honest user gets locked out. For example, in the comic below, the user is having trouble remembering which letters were capitalized, which number substitutions were applied, etc. The key insight behind DALock is that honest user mistakes tend to look very different from the guesses of an online attacker. An online attacker will try to maximize the success rate by checking globally popular passwords such as password, 123456, and let me in. By contrast, honest user mistakes tend to be typos, small variations on the base password, or passwords from different accounts. In the example below, the honest user generally remembers the password, but is trying to recall which number substitutions were applied and whether or not the first letter was capitalized or not. None of these incorrect login attempts are particularly popular. So the key intuition behind DALock is that lockout decisions should consider the popularity of incorrect logins. Here, DA from DALock stands for distribution aware. From a security standpoint, our goal is to quickly lock down a user account after an attacker submits several incorrect or popular guesses. From the usability standpoint, the goal is to avoid locking out honest users as long as their correct login attempts are not too popular. Now is a good time to comment on Stop Guessing, a concurrent and independent work by Tian et al. The key insight is similar. Password popularity differentiates attackers' guesses from honest user mistakes. However, the focus in their work is a bit different. Their goal is to identify and block malicious IP addresses, while our focus is primarily on protecting individual user accounts. Let's just illustrate the performance of DALock under 2 scenarios. In the first example, if the authentication server adopted a 10 strikes policy, then the attacker will successfully crack the user's password on guess 7. By contrast, DALock will quickly lock down the user's account after just 2 very popular password guesses. In this case, the attacker won't successfully crack the user's password. On the usability side, consider the following example. Here we have an honest user, John Smith, who is trying to remember the correct format for his password. Clearly, John Smith generally remembers the correct password, but can't remember the correct format. If the authentication server adopts the 3 strikes policy, then in this case, John Smith gets locked out before he figures out the format for the correct password. However, DALock allows John Smith to avoid getting locked out, since none of the incorrect logins are globally popular passwords. More formally, the DALock mechanism works as follows. We have 2 thresholds, the hit count threshold, psi, and the consecutive strike count threshold, k. For each user u, we keep track of the current hit count, we'll call it psi u, and the current strike count, we'll call it ku. Whenever a user logs in with an incorrect password, we increment the consecutive strike count, ku, and we also update the hit count based on the estimated probability of the incorrect password, pw prime. So here we'll assume we have some frequency oracle, which gives us an estimate of this incorrect password guess. Finally, on an incorrect login, if either the hit count threshold or the consecutive strike count threshold has exceeded their given thresholds, then we'll lock down the account. When the login attempt is correct, we will reset the consecutive strike count parameter. However, the hit count parameter is not reset. So observe that the traditional k-strikes mechanism is simply a special case of DALock with hit count threshold set to infinity. DALock gives us 2 parameters instead of 1 to tune, the hit count and the strike count. The key question is, can we obtain better usability and security trade-offs by tuning both parameters? So, when we instantiate DALock, we need to first specify a frequency oracle to estimate the probability of incorrect passwords. In this work, we developed a differentially private count sketch trained based on actual user passwords. One natural concern in practice is whether or not this data structure would leak individual passwords. So for example, if an attacker can access the count sketch data structure, can they use it to extract individual passwords? We address this concern by adding Laplace noise to preserve differential privacy, and this ensures that the attacker cannot actually use the data structure, even if it's leaked, to extract individual passwords. An alternative approach to developing the frequency oracle would be to instantiate the frequency oracle with a password strength meter or a password cracking model. We consider both approaches in this paper. The advantage of the alternative approach is that we don't have to train the model based on actual user passwords. The disadvantage, though, is that the frequency estimates tend to be a bit less accurate. When modeling an attacker, we seek to follow Kirchhoff's principle. In particular, we assume that the attacker knows about the DALock mechanism and can adapt his strategy accordingly. Intuitively, the attacker's goal is to maximize the probability that a password is cracked before the account is locked or before the password cracking campaign ends. And to model the attacker, we introduce the password knapsack problem to model an attacker who knows the system and optimizes its attack accordingly. As a few examples, the attacker will try to exploit inaccuracies in the frequency oracle. This means that passwords whose true probability greatly exceeds the estimated probability are prime targets for the attacker. So the password knapsack problem is as follows. We first model the attacker strategy by specifying a set T and a holdout password PW hold. And the basic strategy is that the attacker is first going to guess all of the passwords in the set T, followed by the final password guess, final holdout password guess. Here, we're going to require that T is less than some parameter MT. Here, MT denotes the maximum number of guesses that the attacker can sneak in by time T, given the strike limit K and the user's actual login pattern. So the attacker's goal, of course, is to maximize the probability that it cracks the password. In other words, maximize the probability that the user's password lies in the set S, subject to the constraint that the first, all the passwords in the set T, excluding the holdout password, cannot exceed the hit count threshold. So if we sum all the passwords in T and use their estimated frequency, this can't take us above our threshold psi. Now notice that the holdout password is excluded from this sum. So an optimal attacker will oftentimes take the most popular password as the holdout password, since there's no constraint here on this. In particular, the holdout password can take us above the hit count threshold. The attacker won't be able to try guesses after this, but beforehand that's okay. So we conducted empirical simulations to evaluate the security and usability of DALock. Due to time limitations, I cannot describe all the details of these simulations. Briefly, we simulated 1 million user accounts over a 180-day period with and without an attacker. For usability, we measure the lockout rate when accounts are not under attack, and for security, we measure the percentage of accounts that were compromised by the attacker. So this plot shows the usability security trade-off we obtained based on the RockU password distribution after removing the most popular 10,000 passwords. The y-axis here shows the percentage of accounts compromised by the attacker, and the x-axis shows the percentage of accounts that were locked down even when no attacker was present. We first highlight the 10 strikes mechanism. Here, the unwanted lockout rate is almost 0, but the percentage of compromised accounts is quite high. By contrast, the 3 strikes mechanism has a lower, though still substantial, percentage of compromised accounts, but the unwanted lockout rate is quite high. By adopting DALock with a differentially private count sketch, we obtained a superior usability security trade-off. For example, by setting our strike threshold to 10 and tuning the hit count parameter appropriately, we were able to obtain an unwanted lockout rate and compromised rate, which are both very close to 0. However, it's important to ensure that DALock is instantiated with a reasonably accurate frequency oracle. In this case, the neural network frequency oracle is not very accurate, leading to inferior usability security trade-offs. So in conclusion, we introduced DALock and demonstrated via simulations that it can offer a superior usability security trade-off. We recommend implementing DALock with a differentially private count sketch frequency oracle or with the ZXCVBN meter, password strength meter, if no training data is available. We also recommend combining DALock with a ban list since we obtain the best usability security trade-offs when banning overly popular passwords. Finally, in the future, we hope to evaluate DALock in practice. If you are interested, please come talk to us. Thanks for listening, and I look forward to taking your questions at the conference.